Hey everybody, Dr. Sagrin here. I'm bringing you another lecture on global warming. I'm recording this one from my home today, and I guess we better get an obligatory dog cameo out of the way. Hey Loki, hey, you're on camera, buddy. It's actually Loki's birthday. He's 2 years old today. All right, Loki, you ready to learn some about global warming and climate change? It looks like it. And little Luna here is also ready. She's also 2 years old today. My brother and sister, same litter. All right, girly. All right, so we have been talking about climate change and all these different aspects of it, and we've started to get into making some predictions about what's going to happen with it and what's already happened with it. So already we've covered sea level rise and how as the planet gets warmer, ice melts, oceans rise, the oceans thermally expand as they get hotter. And today we're going to add to that some of the changes that we're going to see around the world. Today we're going to focus on wind and the rains that wind carries, and also how that's going to affect life on Earth, both for humans and also the rest of everything else. Let's get right to it. All right, so as a reminder, in one of these earlier lectures, we talked about how Earth is being heated up by the sun, but because of the angle of the sun's kind of rays hitting the Earth's surface, the equator of the Earth actually heats up a lot more than the polar region, which creates this kind of heat imbalance on Earth, where we see around the equator, things get really warm, and up towards the poles, and north and south poles, they get really cold. When you have a heat imbalance, you can look at it, if you put in a tank of water, you have hot water on one side and cold water on the other side, and you just set them in a container. The hot water basically moves to the surface and the cold water pushes underneath, and we call that convection. So having this uneven heat distribution on Earth in terms of both the water and the air basically causes both the water and the air to begin moving around. Cold water sinking to the bottom, cold air sinking to the bottom, hot air, hot water rising to the surface and pushing northward. And that's exactly what we see in the world. We see these wind patterns that are driven by this convection, this heat imbalance, and we also see an ocean current that is driven by the same heat imbalance. When I introduced this, I said that the big question mark here is that as we add more heat to this, and as this kind of imbalance grows more and more, what exactly is going to happen to this wind and also the ocean currents? Now, it might not sound like a big deal to shift the wind or the ocean currents around, but pretty much all life on Earth currently relies on the current status of wind and ocean patterns to survive. And as a reminder of that, we can talk a little bit about biomes. Biomes are regions of the world that have distinct climates, so in terms of their temperature and rainfall, and therefore host a distinct set of life forms. So for example, we can go down here to Brazil, and we see there's a tropical rainforest down here. We look at our color key, and we would expect to find the sorts of plants and animals that live in a jungle. If we went way up here to northern Alaska, we would expect to find tundra and a very different set of plants and animals living there. You would not find polar bears in the tropical rainforest, and you wouldn't find parrots in the tundra region. And the reason for that is because all of these plants and animals are adapted to live in a specific climate. And climate entirely depends on temperature and rainfall. So the rainforest down here is much warmer and much rainier than the tundra up here in northern Alaska. If you somehow could snap your fingers and make Brazil, if you could make it super cold and super dry, it would turn into a tundra. And likewise, if somehow you could snap your fingers and make Alaska super rainy and super hot, it would eventually turn into a tropical rainforest, as these different plants and animals kind of colonized in and began living there. So we know things are getting hotter, and kind of the big question is, how is this extra heat going to affect the wind, the rain that the wind carries, and then therefore the life that depends on those kind of consistent temperatures and rainfall amounts for each region. What we're already beginning to see is that these biomes are actually beginning to move and shift. For example, if we go here to northern Canada or Alaska, right on the edge of this, which is called the taiga, and taiga are kind of this, if you think of Christmas trees, imagine a Christmas tree forest that's pretty cold, but it's not so cold that the trees can't survive there. And then if we go a little bit further north, this is the tundra. This is a place that's so cold and also pretty dry that trees can't survive there. But what we're noticing is that this boundary between taiga and tundra is actually slowly moving to the north. And that's because as the tundra is heating up and warming up, trees at this boundary can survive more and more, and slowly those trees are marching ever slowly up further and further north. We can kind of visualize this. So here's our taiga over here, our Christmas tree forest, and here's our tundra over here where we have no trees, and you can see the ground's very frozen. And so presumably the seeds of these trees are landing here. So you can imagine a seed of a tree landing here, but at this location it's so cold, the ground is so frozen that the trees don't really survive very well. This is a bit of an exaggeration, but that's how it works. And so in between the taiga and the tundra, you kind of have this zone where you kind of have a mixture. And you have some trees, but usually they're a little bit smaller, a little bit stunted, because it's a little bit too cold for them to grow there. But as this region, the entire region is getting warmer and warmer and warmer, more and more of these trees that are warmer weather species are surviving and growing and thriving, laying more seeds that produce more and more trees, and slowly but surely we can imagine that as this gets warmer, this entire region could be covered in trees soon. And what that looks like kind of from above is that the forest is actually moving and shifting in one direction. So already we are starting to see things like that happening in the world, and that just mainly depends on temperature. But the other main factor here is rainfall. For example, if we go to this part of Africa, is probably the best example of it in the world. Here in Africa, this region is super rainy, and you have things like rainforest and other kinds of forest. And this region, not very far away, is bone dry. It's one of the driest places in the earth. This is the Sahara Desert, the largest desert on Earth. The difference between this spot right here and this spot right here isn't really a matter of temperature. Temperatures can rise and it doesn't really affect it. The main difference between these two locations is rain. And so are rainfall patterns going to shift around the world? That is a very, very big question in science right now. And the answer is yes, rain patterns are already shifting in the world. And if we look back in the past at our paleoclimate data, we can see that rainfall patterns were different in the past during warmer periods of time as well. And so that's the bulk of what we're going to be talking about here, is how is this rainfall going to change in the world? How are these biomes going to change? How is it going to affect life on Earth? And how is it going to affect us, humans, trying to live here as well? Before we talk about all that and how rainfall patterns is going to change in the world, it's important to talk about what actually causes rain and deserty areas in the world in the first place. For example, here is a desert, really massive desert. If we're looking at this key, places that are kind of either white or gray or pink on this map are drier, and places that are blue or green are wet. So you can see that there is a really massive dry belt that extends through this region. This is a super dry area. And right beneath that dry area, pretty much everywhere that it borders, there is a super rainy area as well. So this is, let's go change color here. So in this region, we have tons of rain. over here in Central America and South America as well, you have lots of rain. And so you can kind of see that there's this sort of pattern where you have lots of rain in this one region, and then you have lots of dryness in this other region right next to it. And then even down below that in Australia and South Africa, you can kind of see another pattern down here. It's like dry down here as well. So you kind of get these different rainy and dry belts in the world. And well, why does this happen? I mean, the temperature change between these different regions is not all that significant. So why do we have these kind of rainier and drier belts forming in the world? A bit peculiar. Something else that I'd like to point out here is that America's rainy and dry belt kind of goes the other direction, and it's a different situation here. But you can kind of see that the western half of America is pretty dry, with the exception of the coastline of like Oregon and Washington and Northern California. And generally the east side of America and the North America is rainier. It is a bit peculiar when you look at this map. It's like exactly what is producing this, and I think the best way to actually explore this topic, I'm not a meteorologist, so I can't give you tons of detail about these patterns specifically in terms of wind and all that stuff. But there is a really cool website that you can really visualize these patterns, and it's all pretty much driven by wind. So if you really want to understand why it rains in certain parts of the world more than others, you really have to look at global wind patterns and also the distribution of ocean temperatures. And that is what this really cool visualization and this really cool website does. I'll make sure I link this website in the YouTube description. It's kind of mesmerizing, but basically what this map is showing is the different colors you see in the ocean are corresponding to temperature. Red is a hot ocean, and yellow to green to blue is a cooler and colder ocean. And then over the top of that, you can kind of see these little swirly marks. And those are indicating how the wind is blowing about a mile up in the world, which just happens to be the elevation that rain clouds typically form at. So why do we care about ocean temperatures if we're talking about rain? The reason for that is a huge amount of the evaporation that happens in the world is going to be happening over oceans. So as oceans are heating up, the water is evaporating, and that's creating water vapor that can form into clouds, and eventually, given the right circumstances, can form into rain clouds that bring rain to a location. So how the wind is blowing over the ocean, in particular how the wind is blowing over a warmer ocean, can really show you what areas of the world are likely to get a lot of water vapor blowing over them. And if the conditions are right, that water vapor can condense into clouds and rain on them. So let's look at the United States first. And I had just mentioned that the United States has this kind of divide to it, where if we kind of take the exact center of the United States, the western side here is pretty dry and the eastern side is pretty wet. This just happens to be how the wind is blowing right this second as I'm recording this lecture. But even here, you can kind of begin to see what is going on. We can see at the moment there's pretty strong winds happening in the east. We have this kind of big swirly motion going on that's bringing some cold air down to the south. We have a super hot ocean, the Gulf of Mexico and the Caribbean Ocean here to our south. See, there's some pretty strong winds blowing from east to west here. And right in the middle, you can kind of see that the cold air, strong cold air kind of blowing in from the north is mixing with this warm, wet air blowing in from the south that's coming over this really hot ocean. And where they're kind of mixing, You can see everything's kind of slowing down for a second. And that would be generally a pretty good indicator that this hot air that's blowing off the ocean is going to be cooling off and kind of sticking in one spot. And there's a pretty decent chance that there is rain in this region, I would guess right now, which is over the Gulf of Mexico. And sure enough, if we check the radar map, there is rain right there. At this particular time, the rain is kind of out here, but many times during the year, and actually just like earlier today and last night, the point of mixing between this warm air coming from the south over the ocean and this colder air coming from the north is in this region here, which is why this area is typically pretty wet. Conversely, over here on the drier side of the United States, we see that there is an ocean, the Pacific Ocean over here. The winds aren't quite as strong coming off of that ocean. And so because it's a colder ocean, considerably colder, we would expect less evaporation happening and the generally weaker winds. And also we have many mountain ranges in this area, the Cascade Mountains, the Sierra Nevadas, the Rocky Mountains. This wind that's not carrying as much moisture that's blowing this way typically doesn't penetrate as deep, and generally speaking, we don't get as much rain. This coastline here gets some rain, but after that, it's pretty dry. And so already you can kind of see, okay, it really does just have to do with oceans, whether or not the ocean is kind of warm or cooler, and then also how the winds are kind of blowing off of the ocean and into the land here. That's determining which side of America is wet and which side is generally dry. Conversely, we can see that similar patterns through the rest of the world. We can see that this area of Africa right here in the northern Africa, where this massive desert is, most of the wind here isn't really blowing off of any ocean in this central area. It's really far away from an ocean. And then the ocean where some of these winds are actually blowing off of are generally a little bit cooler. The part of Africa that is really has lots of rainfall typically has this really hot ocean next to it, and the winds are penetrating a bit, but not far enough to get to the desert region. So all along the world, you can kind of see similar patterns like this that are emerging. Honestly, I could look at this kind of all day. One of the clearest examples where you can see the effect of a really hot ocean and the winds blowing just the right way would be down here in Indonesia and Australia. These islands are some of the wettest islands in the world. New Guinea and Indonesia and Malaysia, Philippines, tons and tons of rain to here. And you can see why. You have this massive ocean that is super hot. It's so hot here, it's even a little pinkish. You have these winds blowing strongly. When the winds hit this land, they slow down, they cool off a little bit, and it drops a lot of rain. Right next to it, Australia, pretty dry. You can see a bit of this rain is actually coming down towards Australia today. Sorry, a bit of this wind that's carrying this moisture. But most of it doesn't actually penetrate into Australia very much. It kind of gets diverted around to those islands. This tip of Australia is actually pretty rainy. But the middle of Australia, you can see the bulk of the wind is actually coming from the Antarctic Ocean. This is a very cold ocean, not a lot of evaporation going on. And so, yes, there's wind blowing over Australia, but it's not going to have much water vapor to it. And I'm curious, I wouldn't be surprised if there was some rainfall over on this section of Australia today. But this middle section, I would guess, is not going to have much. Let's see what's going on there. And yeah, you can kind of see that. The bulk of Australia has very little rain. Most of that moisture was getting diverted down to the south. And yeah, New Zealand and those areas were probably getting some moisture, but none of it was really penetrating into Australia. And up here where all that rain was blowing over, you can see this area is just pretty constantly a stormy area of the world. So to kind of explain that, generally our rain and desert belts, places in the world that are rainy are typically next to warmer oceans, and they have winds that kind of penetrate from those warmer oceans into the land. Generally, where we find places that are deserts, there's either not much warm ocean nearby, or those warm ocean winds don't penetrate into the coast very well. So with that in mind, what's happening let's talk about the United States first. What's happening to our rainy and dry belts? So again, when we were looking at this United States map, we can see that the eastern side of the United States typically gets a lot of rainfall, in particular where those warmer ocean winds kind of blow off of this really, really hot ocean, the Caribbean and the Gulf of Mexico, and where they mix with some colder air coming down from the north. Typically, that's where you get lots of rain. When we go over to the western side, we have an ocean, but it's much colder. So this is a much colder Pacific Ocean over here. There is some wind that's kind of penetrating in, but it's not going to carry as much vapor. And there's all these mountains in this area. The whole area is very mountainous. The rain can't really penetrate through those mountains very much. So yes, we get one really rainy area, but the rest is pretty much bone dry. So what's going to happen? Any changes at all can we expect in the United States in terms of, are the drier areas going to get rainier, or are they going to get drier? Or are the rainy areas going to get rainier? Or the rainy areas going to get drier? We know everything's going to get hotter, but what's going to happen with the rainfall? And as a reminder, as we go through this content, this is the biomes map for North America. So you can see that the area that's really dry, this is a semi-desert or a grassland, places that typically don't get enough moisture to support forest. And over here on the rainy side, we typically get cool, warm temperate forest or cool temperate and mixed forest. Then eventually, as you go further and further north, those differences don't matter as much and aren't as relevant. All right, so this shows us what's happening to the United States. The temperature map is very alarming. Obviously, we've been talking about how things are getting hotter and hotter and hotter. If we look at temperatures from 1961 to 1990, we can see compared to the average for the century, they're pretty normal. A little bit cooler here in the southeastern side, a little bit warmer up here on the northwestern side, but nothing too extreme going on from 1961 to 1990. But then here from 1991 to 2020, you can see everything pretty much everywhere is getting considerably warmer by more than 1 degree, more than actually 2 degrees Fahrenheit, probably pushing 3 degrees Fahrenheit for most of these areas. But actually this rainy area is not warming up as much, and that is because the rain actually has a pretty massive cooling effect on regions, climate, and temperatures. So that's kind of nice. Unfortunately, where I'm in Houston, we are right on the edge of where it's getting hotter and hotter and hotter. Let's look at rainfall. We can see that the changes with rainfall aren't as extreme, but they are getting more and more extreme there as well. From 1961 to 1990, for the most part, everything was pretty average. We get a little bit more rain here, here, a little bit drier here. But for the most part, everything is pretty neutrally colored. Whereas when you go from 1991 to 2020, and this data just was published by NOAA a few days ago, we can see that these extreme changes become larger. The entirety of Arizona and Southern California are pretty much in a very extreme drought where we're getting less than 10% of the average rainfall. So this is really, really dry over this 30-year period compared to the previous century. And conversely, kind of on the wetter side of the United States, the north Midwest and Michigan, so up here in the Dakotas and Nebraska and Iowa and Wisconsin and Minnesota, those areas are getting really, really, really wet. And so is my little neck of the woods here in Houston, actually. And that's probably because of increased hurricanes that are stalling over our region and dumping tons and tons of water. That might be enough to shift some of that difference. And that just keeps seemingly happening to us. But we can see that overall, the pattern is the dry side of the United States overall is getting drier or holding steady. Some places are getting super dry. And the kind of rainier side of the United States, the eastern side, if anything, it's getting rainier and rainier and rainier. All right, so the drier areas are getting drier and the rainier areas are getting rainier. Okay, how's that going to affect life in these regions? Well, it's hard to predict those things, right? Yeah, we would expect biome shifts and things like that. If there's a grassland that is getting drier and drier and drier, it might turn into a desert. Same with the forest. If there's a grassland or a desert that's getting rainier and rainier, then it might eventually turn into a forest. Things like that we can expect to happen. But it's hard to predict exactly how those would happen and how fast for the amount of warming that we're seeing. And so once again, our good friend paleoclimatology can actually help us understand this issue. Paleoclimatology is the study of the Earth's past climates, and we have some really good data in North America for the last 20 or so thousand years about really specifically what the climate was like in different regions. The interesting thing is that over that 20,000 year period, we were in an ice age where things were really cool. It warmed up considerably up until about 5,000 years ago or so. And then in the last 5,000 years, it had been cooling very slowly. Now it's warming very fast again. So we can look back at those cooler periods and the warmer periods and say, okay, in those times, how did rainfall and climate change? And how did that change the life that was living in these different regions? All right, first off, how can we have such detailed records on what the climate was like in the last 20,000 years? In particular, how could we possibly know how much it was raining in the last 20,000 years ago? And the answer comes from pollen records. Pollen is basically the stuff that's made by trees for reproduction purposes. It's basically plant sperm. And the plants basically broadcast it in the air, and then it can land on other flowers and other plants and whatnot to create seeds. I know it's kind of gross, but that's what pollen is. And the pollen, everybody knows pollen season, you get tons and tons of pollen in the air. Most of this pollen either, does its job or it kind of gets decomposed in soils. But if it happens to land in a lake, it can sink down into that lake, into the lake's sediments and get buried in layers and not get decomposed. And so we can dig into these layers at the bottom of the lake and actually find pollen traces in these different layers. We can figure out how old the layers are from a variety of different ways. And what ends up happening is that we have this very detailed pollen record over time. Older sediments are going to be farther in the past, younger sediments are going to be more recent. And so what we see is that at certain points of time, we might see a pine tree that was typically found, again, nothing has really evolved in the last 20,000 years. I mean, that's a pretty short amount of time for evolution. So if we see a certain species of pine tree that we see today, and this pine tree lives in a very dry environment, we can assume that at this point in time, this location was dry. If we see a oak tree later on that is currently living in a much wetter environment, so we assume back then it would have lived in a wetter environment as well, we can assume that at this period in time, this area was more rainy. And so we can actually reconstruct both how hot it was and also how rainy it was based off the kinds of trees and plants that were living in an area. And what we see is that things have changed a lot in the last 13,000 years in terms of what was living where. Around 13,000 years ago, we were coming out of an ice age, and a huge chunk of North America was still frozen. And so you can see this giant block at the top is ice. And then you have some tundra around that ice. We have a desert here also, again, on the western side of the United States. But we'll look, this desert is considerably smaller and shifted further to the north than it is. And we have a tinier grassland here in the center, that's the yellow color. the taiga, the Christmas trees, extended all the way down almost to Texas. So that kind of Christmas tree snow forest would have made it all the way down to here. And then once again, the Gulf Coast would have had warm temperate and a bit of cool temperate forest in that area as well. Ooh, Florida was a scrubland. That's interesting. So this was probably a bit drier. So you can see that a lot of things changed, and this was a period of time where the Earth was cooler, and generally speaking, if we look across the entire continent, it was a bit drier. So, okay, if we were wondering what's going to happen if it got cooler, this would be very helpful. Unfortunately, right now, things are getting much hotter very fast. So we want to know, okay, what are these biomes going to look like as it gets hotter? So this was again, this is 5,000 years later, and this is a reconstruction of Pollen Records 8,000 years ago. And this was close to what's called the Holocene climatic optimum, but actually not quite. And unfortunately, I cannot find a map of the true climatic optimum for North America, which would have happened between 3,000 and 5,000 years ago. I have a partial map, and we'll get to that later, but this is kind of close. And we can compare, so this would be a period of time where it was warmer, not by that much, maybe by a half a degree from where it is now, but it held there for a really long time, so the different biomes had a chance to change. And we can see, you might look at this and say, well, that looks pretty much the same as what we got today. There are some tiny changes. So again, this is, we can compare this one, the Holocene climatic optimum, or close to it, when it was a bit warmer, to today where it's technically a bit cooler, but currently warming really quickly. So biomes haven't really shifted much at all because the warming has been so rapid so far. But this would be back to slightly more cooler. Again, would be this, the present day. And so what's the difference here? Doesn't look too different. There are a couple things that you can see here different. The desert here, present, is smaller than it is when it was warmer. So you can see, in particular, we want to look right here at this location. So we can see that 8,000 years ago, this would be roughly Central California was a desert when it was warmer. And currently, if we look at that same location, it is a grassland or a forest. So that desert in the last 8,000 years has shrunken as we've gotten cooler. But as we get hotter, chances are it's going to begin expanding again. We can see something kind of similar here. Up here in this northern area is a what's called a steppe. That's kind of a mixture of grassland and forest. So this could considerably have been a little bit drier as well. It might have just been colder because it was coming off this ice age, and so the forest hadn't had a chance to grow in yet. But needless to say, we can also see here in this region of Mexico, we can see a bigger desert, and also into this region here. So our current trends that we're seeing, that the Western United States is getting drier over time, that seems to be confirmed by paleoclimate data. So as things are heating up on Earth, the Western United States is currently getting drier on that trend. And if we go back to paleoclimate data to a period of time when the Earth was a little bit warmer than today, it was also drier. So we can expect the desert region here of the United States to just keep getting drier and drier as it gets warmer and warmer. The reason for that is these winds that kind of blow, even though this is a cooler ocean, the winds that blow off of this coast, as things heat up, they get pushed further and further to the north. And so this area to the south gets drier and drier as a consequence of that. And currently we are seeing that as well. All right, you might be thinking to yourself, oh my God, this guy's been talking already for a long time. He's talking about how things are going to get drier in certain part of the world I'm not even living in. Who freaking cares if it gets drier over in the desert of, the Western United States? And part of that answer is that it's not just the desert parts that are getting drier. Parts that are currently grasslands and forests are going to get drier and drier and turn into deserts potentially. And the reason why we should care is that people live there, first of all, and they're seeing all kinds of issues with climate change already. But secondly, and something that you might not realize, is the biggest farming state in the country of the United States is California. In particular, there's this valley called the San Joaquin Valley that has been in a drought for about 15 years or so. If you look at the average rainfall over the last 15 years, I think it's about 5 inches lower than normal, 4 or 5 inches below normal, which corresponds to around 20% below normal. And the reservoirs and the lakes that are supposed to hold water that we can use for irrigation for our farming are drying up really, really rapidly. And more farmers are having to resort to pumping groundwater out of the ground. But even that's beginning to run out as well. And so, yes, you have these areas where farmers have kind of given up that used to have these massive, this is a grape vineyard here, a picture on the right. So this would have been this lush farm with all these grapevines growing on it. And now it's basically looks like a desert. Something else we're seeing in California is along that same valley where it's getting hotter and hotter and hotter, but also less rain is falling, is increased numbers and frequencies of forest fires. If I were to ask you, okay, let me go back to this biome map here. That first area that I was showing, this is the San Joaquin Valley right there. And again, 5,000 to 8,000 years ago, that same area would have been desert, not grassland. So if I were to say, what would it look like for a region of the world that is currently a grassland or a forest to kind of slowly or maybe even rapidly turn into a desert? What would that look like? I think these two pictures basically sum it up, right? It seems like more people are also catching on to this. I just read this in a newspaper the other day. It was an article that was called "There Is No Drought," and they were talking about California. And I thought, oh, maybe this is some kind of like anti-science thing, but no, they agree with all the science of global warming and all that stuff. They're saying we should stop calling it a drought because, and here at the bottom, if drought means a period of time, a period of dry years that are followed by a return to the normal, California is not in a drought. This is just the new normal. The idea is that the climate is shifting in such a way that there is not going to be a time where the rainfall returns, and slowly over time it's just going to get less and less rain. And humans have come a long way, but the idea that we can farm in a desert, I think, is still kind of a long way off. So yeah, that's just to kind of show you that this stuff is really, really important. Tons of food are potentially at stake. Maybe you're saying we can grow this food somewhere else, possibly, but possibly not. So really, really big things are at stake here when you're talking about changing the rainfall in the world. Speaking of which, on the flip side of the United States, where you might be thinking, oh, well, yeah, California and Arizona, those places are kind of screwed, but at least here on the eastern side of the United States, we're doing okay. Well, you know, too much rain can be also a bad thing, especially for farming. If you have crops that aren't meant to be flooded with water and they get flooded with water, that can ruin your crop. So hurricanes and big storms coming through the eastern side of the United States can also be problematic. I would love to go through each region of the world as detailed as I did for North America and for the United States. But unfortunately, I don't want to make a 20-hour video. So I better wrap this up soon. But this is the overall global outlook of the United States. These are the projections of what's going to happen with rainfall according to the kind of worst warming models, which I think are likely to be happening. So we can see our actual neck of the woods here is actually not too bad, where you can kind of see this little dry area and the little wetter area over there. You can see that that's actually a pretty subtle change here that they're expecting. Right now it's more extreme, but we'll see if it kind of evens out in the future. But you can see a very, very extreme changes in other parts of the world. The biggest in terms of more rainfall, we can see a giant blue swath over here in the Pacific Ocean. That is just as this ocean gets hotter and hotter and hotter, it's going to produce more and more evaporation, and that evaporation will result in rain clouds forming and more rain there. The good news is that nobody really lives there, so not too big of an impact on humans. The next biggest area where we see more rainfall is up here in the Northern Hemisphere. That's probably likely going to be more snowfall and more rain coming to the northern latitude regions. Again, not a ton of people live up there, but it will have some effects on those ecosystems, the tundra and the taiga and whatnot. But probably the biggest change here that's actually going to be potentially meaningful to people is going to be in this region here. North Africa, that Sahara Desert, and also Saudi Arabia, this massive desert region, as things get hotter, these oceans, as they heat up more and more, normally the moisture from these regions doesn't penetrate very far into the continent, but as it heats up more and more, it can penetrate further and further in. And so we expect more and more of this moisture to creep into these desert regions, and that's we're pretty confident in that. And we are currently already seeing those trends. And actually, if we go back 5,000 years, this area used to be much, much wetter. It was not a massive desert back then. So we can expect that change. On the other flip side of the dryness changes, we can see that Southern Europe is the one area that's going to get drier and drier over time. And that is a big deal because there's also tons and tons of agriculture in that region of the world. And currently we are seeing those trends, especially in the north of Spain and also in Turkey and the Middle East, so in this region. So it'll be interesting to see if those continue. One kind of bizarre fact of this North African region getting more and more rain that seems to also begin happening in the world is that locusts live in these regions, something called the desert locust. This is an insect that kind of lays eggs in the desert, I presume, and then when there is a big rainfall event, the kind of insects hatch and they kind of feed on any kind of vegetation that grows, and then if enough of them grow, they can actually form what's called a swarm. And to see what's happening lately this is from the Saudi Arabia, this is the Arabian Peninsula, the Arabian Desert. They were hit by basically a hurricane that carried a lot of moisture in it, and this desert region basically came alive. You know, what was a desert full of sand dunes basically flooded and created all these little lakes, and then all this algae and vegetation began growing, and as a result of this is what a locust swarm looks like. So they're kind of like grasshoppers. But yeah, when it rains in the desert, they just pig out on all this extra food that they're getting, and they form this massive swarm. And these swarms made it down to Kenya, over to Pakistan and India, up to parts of Italy, and throughout the Middle East and Northern Africa, and they just eat all kinds of vegetation in the process. Locusts were not something that, every once in a while there'll be a kind of a locust swarm, but in 2020, all kinds of folks were saying it was the worst locust season they've ever had. It was certainly the first time I'd ever remembered seeing anything about locusts in my lifetime, that there were massive locust swarms in the world. And again, it has to do with this region getting more rainfall to it. And if this increasingly becomes the more new normal, we could expect this region to eventually transition to a grassland potentially. and it's unclear what that will do to the locust populations of the world. One last little subject I want to cover is that we see that overall, some places in the world will get rainier, some will get drier, but the overall trend is that a warmer world is generally a rainier world, because as you heat up things, you heat up the ocean, it generates evaporation, more water vapor, and so we can expect more heat is more evaporation, more rain. And it doesn't always translate to consistently more or less rain for any particular region, but what we can expect and what we are already seeing all over the world is that you have higher chances of super heavy precipitation. So percent change in heavy precipitation would be precipitation that could generate something like a flood event. And you can see that pretty much everywhere in the world is on the blue side rather than the white or orange side. So blue side means higher chances of flooding in the world, and the polka dots on this map are places that they're pretty much 100% confident this is going to happen in, and it's already happening. If we look at natural disasters over time, we can see some changes in the frequency of natural disasters. The tiniest change are geophysical events. Those are related to plate tectonics, so we shouldn't expect too big of changes over time with something like that. And yeah, sure enough, this red line is pretty flat. It's going up maybe very gradually. There could be an explanation tied to global warming, actually, but we won't get into it. Then we can see other events, meteorological events like hurricanes and tornadoes. Those are increasing. Again, those are all heat-driven processes. Climatological events like extreme heat waves, drought, forest fires, those are increasing close to double as more common today than they were 40 years ago. But the one that's really shooting off the charts here is the floods. Floods are becoming way more common in the world. Currently roughly four times more common than they were 40 years ago, according to this data. And that should be familiar. I mean, me living in Houston, already in my lifetime, we've had basically two worst floods in Houston's history, Tropical Storm Allison and Hurricane Harvey. And it's not too surprising that we are getting these bigger hurricanes and more frequent hurricanes in the United States. And also, the fact that they are causing bigger and bigger floods is potentially related to climate change. It also has to do with poor flood planning and poor city design and all kinds of other things. But let's get into a little bit of the science of hurricanes and talk about how they might be affected by global warming as well. Hurricanes are basically heat-driven processes. When an ocean gets really hot and the winds are blowing just right, this hot water, this hot evaporation basically creates this massive swirling storm, a hurricane. And as you add more heat to it, the hurricanes should get more and more powerful and potentially bigger, or you can have more and more hurricanes. So oceans are getting hotter, we can expect more hurricanes and potentially bigger hurricanes. And that is actually the trajectory that we are seeing in the Atlantic Ocean. If we go back to the last 140 years, we can see the overall trajectory is, yes, we are getting more and more hurricanes. And apparently there's some different climate patterns that result to kind of more and fewer and more hurricanes. But overall, despite this, you can see the overall trajectory is upward. Same thing is happening in the Pacific Ocean. Places like the Philippines are getting more hurricanes than they've ever had as well. So yes, we're getting more hurricanes. Another phenomenon that I just want to close here with is that hurricanes, a lot of modern hurricanes are tending to do what's called stalling, and that's what Hurricane Harvey did. So we'll look at a couple of examples of hurricanes, kind of what's a typical hurricane path versus a stalled path. But ultimately, this stalling has to do with what's called the jet stream. The jet stream is a wind current that is moving pretty high up across North America and pretty fast. So it is a many miles up, 5, 10, even maybe more miles up in the atmosphere. But it basically is a really fast moving wind pattern that sweeps across the United States, sometimes higher, sometimes lower. But what we're finding is that, and this is now scientifically verified, that statistically speaking, the jet stream, as the planet is heating up more and more, is becoming what's called wavier. And this waviness is actually what helps create these cold fronts. So when you have a big wave, it basically lets cold air come shooting down. One way that you can think of this is that the jet stream is kind of what's protecting the cold air up in the north from making its way down to the south. It's kind of this little bubble of protection for us. And when you have big pockets of heat buildup due to global warming, it can kind of bulge this jet stream, so it becomes wavier. And so yes, the cold front that just happened, the insane cold front that happened in February, was also caused by this wavy phenomenon. But this phenomenon also causes stalled hurricanes, and I'll show you how. This is a typical hurricane path. So this was Hurricane Laura that just happened. I just picked this one. It just happened in 2020, a few months ago. This is one that it was looking like it was going to hit Houston potentially, but then it kind of sharply veered. And you kind of notice it's pretty interesting that this hurricane is kind of drifting, and then it kind of hits a point where it really veers hard this way. And what's happening is it's kind of, in my terms, it's kind of getting sucked into this strong jet stream that sweeps across the United States. And so when you have a really, really strong jet stream, basically these hurricanes can hit, but when they do hit, they kind of get pushed out pretty quickly. They move through really quickly. Yes, you can have some damaging. Obviously, hurricanes are very powerful and they blow the wind and all that stuff. But the hurricane itself is always kind of moving and getting swept away into the land and away from one place. And this jet stream kind of moving fast prevents the hurricane from staying in one place for too long. If we look at the path of Hurricane Harvey, it kind of did this bizarre thing where it was going, and you would expect it to kind of get swooped away, and then it just kind of stopped. And it stopped here for like 3 or 4 days and just kind of like went backwards for a little bit, and then finally it kind of moved on, but very, very slowly. And the reason for that is that the jet stream at the time when Harvey made landfall was doing one of these weird wavy things. And so normally this jet stream, where it would kind of catch this hurricane and kind of keep shoving it away and sucking it out of any area for too long, it kind of did the opposite. There was just kind of, the hurricane kind of got into this area and there was nothing there. It kind of just got stuck. And then actually a little bit of this bulge coming this way kind of shoved it back for a little bit. And then finally, after enough time had gone by, it basically got sucked out when the jet stream kind of normalized. So this warping of this jet stream caused by global warming, and it seems to be getting more and more warped over time, and these warps become more and more frequent, is giving the potential not only for extreme cold fronts that can come down this way as it warps, but also can stall these hurricanes that make landfall when you're in this sort of underbelly of the warping. And this actually happened, I have the slide, this happened this year actually. It just was a smaller storm. Tropical Storm Beta was just this tiny little thing, but it ended up getting stalled and was kind of hovering around Houston for a while, and nobody thought it could generate flooding because it was such a tiny storm, but it actually did generate some minor flooding because it stalled out. So yeah, that kind of explains the potentially increase in rainfall that we're getting in our neck of the woods here in the Gulf Coast. All right, well, that was another long one. Sorry. There's always just a lot of information to cover with these, but just to kind of summarize everything, our planet depends on pretty consistent temperature and rainfall in different areas of the world, and that's what drives pretty much all life that's living in those areas. As we add more heat to the system, it's going to change rainfall and temperature patterns, and it's also going to change what kind of life forms can live in what area. It can also greatly affect humans. So the folks in California, as it just keeps getting drier and drier and drier, and potentially is reverting back to that desert-like state it was in 5,000 years ago. You're going to see more and more forest fires. You're going to see harder and harder times for farmers, and that's going to affect everybody because we need to eat food. And similar patterns might be seen in Southern Europe as well. Conversely, some places might get more rain, and that can be a good thing overall. I mean, rain is generally kind of the stuff that is necessary for life. So we can see deserts come to life again, potentially over the next several decades and hundreds of years. But that can also have unintended consequences like locust swarms and things like that. Last but not least, generally speaking, a hotter, warmer world will bring more rainfall on average to more places, but pretty much everywhere is expected to get more flooding and heavy rainfall due to these warmer temperature patterns, driving more and more evaporation from the oceans. And when you kind of add that on top of this disruption of the jet stream wind patterns, and the idea of hurricanes kind of stalling out over your city and dumping 50 inches of water, we can expect to see more and more extreme flooding events and the likes. So that just goes to show you that maybe you're not super interested in global warming, climate change, whatever, but it's going to affect your life one way or another. So we all need to become interested in it. And what we'll be talking about next time is changes in the oceans. So that was kind of like air and rain. So we'll talk about oceans next. And then after that, we'll be closing out this series with talking about, okay, are there any viable solutions to solving this problem? And that'll be it. So until next time, see you guys later.